Pluto, a far-off and befuddling, more humble planet, was once a solitary individual from our nearby planetary framework's planetary family. However, later upsetting declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a stunning disclosure. They suggest that this cold world is on a potential crash course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we seeing a novel cosmic peculiarity, or is there something else to this approaching inestimable disaster? Join us as we explore the potential outcomes of a Pluto-Neptune crash. Pluto, once thought to be a planet but later downgraded to a dwarf planet due to its inconsistent orbit, remains a subject of interest and study in the scientific community. According to recent predictions by leading researchers, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising alarms about a potentially disastrous crash between these two planets, which could pose a significant threat to Earth. But how is such an event even conceivable? Pluto's orbit around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete one orbit, meaning that since its discovery in 1930, it hasn't even completed a full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its exceptionally elongated shape, completely deviating from the nearly circular orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, tilted at 17 degrees to the ecliptic plane. The path Pluto follows is much more extreme compared to other planets, and this inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its conjunction with Neptune's. For around 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, contrary to what one might expect based on their positions in the planetary system. This raises the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. At first, astronomers tried to understand its unique path compared to other planets, whose orbits are more closely aligned with the ecliptic plane. Pluto's orbit stood out due to its steep inclination and irregular shape. The mystery deepened with the realization that Pluto's orbit does, in fact, cross Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricacies of celestial mechanics. The three-body problem in space concerns the interaction between three objects, such as Pluto, Neptune, and the Sun, and how their gravity affects their motion. It's akin to trying to predict where they will go based on their starting positions and how they influence each other. For Pluto's case, this problem demonstrates how its orbit, Neptune's orbit, and the Sun's gravity all collaborate in a complex way. Terms like asymptotic libration, scope libration, and VSK oscillation are part of this puzzle. According to astrophysicists, what keeps these planets in their orbits is a type of libration, particularly with regard to Pluto and Neptune. Libration, in this context, means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is essential in keeping their orbits from crossing. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, adding an extra layer of protection against potential collisions. Another important factor in this scenario is the VSK oscillation, named after researchers Val, Asimov, and Levkov, who studied the motion of objects in space. This phenomenon concerns how three space objects, like Pluto, Neptune, and the Sun, affect each other's motion through gravity. The gravitational interactions between these objects maintain Pluto's orbit in a stable configuration, despite the apparent chaos of space. The three-body problem helps in understanding how the orbits of celestial bodies can change due to their gravitational interactions. By studying this, we learn more about Pluto, our solar system, and distant stars. Furthermore, mathematical simulations in the late 1980s revealed that despite these stabilizing mechanisms, Pluto's orbit is, in fact, turbulent. Minor deviations in its initial conditions could lead to massive changes over long periods of time. However, these remarkable properties of Pluto's orbit have been found to maintain stability over incredibly long timescales. Later computer models showed how the gravitational pull from giant planets like Neptune, Jupiter, and Saturn affects Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance stabilizes Pluto's orbit. However, Neptune is not the only planet contributing to this cycle. Jupiter's gravity also plays a significant role in maintaining Pluto's orbit, with Saturn also contributing. These simulations suggest that Jupiter's gravity alone is strong enough to ensure Pluto remains on a steady path for an extremely long time, possibly even billions of years. Perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto keeps moving safely through space without running into trouble. These factors are crucial in the broader context of the universe, as they contribute to the stability of celestial bodies' movements. Without such forces, the nearby planetary system would be much more chaotic. Bodies like Pluto could crash into others or be ejected from their stable orbits, triggering a ripple effect on other celestial bodies. For Pluto, particularly, understanding its orbit is essential. This gives us a clearer picture of the dynamic nature of our planetary system. The case of Pluto illustrates how even the most seemingly unstable orbits can reach a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also emphasizes the importance of continuous observation and research to better understand our place in the universe. Exploring the depths of space often forces us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is an ideal example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in the case of Pluto. This means that even small changes in Pluto's position or speed can drastically alter its long-term orbit. Computational simulations have been crucial in helping scientists understand how Pluto travels through space. These simulations use complex mathematics to replicate the gravitational interactions between Pluto and other space objects, such as Neptune. By altering small details in the simulations, astronomers can see how even the smallest changes can result in vastly different outcomes. In the late 1980s, these simulations revealed an interesting observation about Pluto's orbit. Despite having mechanisms like asymptotic libration and scope libration to stabilize it, Pluto's orbit can still be unpredictable. If you start with even a slight difference in Pluto's position or speed, its path can appear drastically different over many years. However, despite this apparent chaos, Pluto's orbit remains stable for billions of years. This means that Pluto's journey around the Sun has an inherent order, even though it may seem erratic at first. Predicting major events, especially those involving chaotic orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term predictions are filled with uncertainties. While mathematical simulations offer valuable insights into the future behavior of celestial bodies, they also highlight the limitations of our predictive abilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they replicate. Any slight error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits like Pluto's serves as a reminder of the constantly evolving and dynamic nature of the universe. While we've made significant progress in understanding space, Pluto's case serves as a reminder that our knowledge of the universe is still limited. Understanding the gravitational effects of giant planets on Pluto's orbit offers valuable insights into the broader dynamics of the nearby solar system. It shows how the position and presence of each planet can have far-reaching impacts on the stability and direction of other bodies within the system. So why are prominent astrophysicists only now raising concerns about a possible crash between Pluto and Neptune, despite all these complex forces working to prevent it? Neil deGrasse Tyson, a renowned astrophysicist, offers a new perspective on the mysteries of our nearby solar system, particularly the fascinating case of Pluto. Tyson, known for his role in renaming Pluto as a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the forgotten corners of space. He sees the renaming of Pluto not as a downgrade but as an important shift in our growing understanding of the many bodies orbiting our Sun. His approach to celestial mechanics is one of constant learning and adaptation. He acknowledges the complexities of Pluto's orbit, as well as its interactions with Neptune, from a perspective that embraces the quirks of space. Tyson suggests that while Pluto's orbit is stable now, it could undergo significant changes in the future. This possibility serves as a reminder of how much we still need to learn about the forces shaping our nearby solar system. In conclusion, Pluto's orbit is a fascinating example of the complex interaction of gravitational forces within our solar system. While its path remains stable for now, the intricate dynamics between Pluto, Neptune, and the other planets suggest that even the most seemingly stable orbits can change over time. As astrophysicists like Neil deGrasse Tyson continue to explore the mysteries of the universe, they help us better understand the delicate balance that governs the movement of celestial bodies. The potential for a Pluto-Neptune collision is not necessarily inevitable, but it is a testament to the ever-evolving and unpredictable nature of the universe. Understanding the scientific theories surrounding Pluto's orbit, it is important to consider the broader implications of these forces for our understanding of the nearby solar system and the universe at large. While Pluto's journey remains a topic of fascination, it also serves as a reminder that the universe is full of hidden complexities awaiting exploration. The concept of orbital resonance, particularly between Pluto and Neptune, is a crucial piece of this puzzle. This resonance, where the ratio of Pluto and Neptune's orbits is 2:3, is a striking feature of celestial mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This ratio ensures that despite their orbits intersecting, the 2 planets never collide. This phenomenon is a result of gravitational interactions that stabilize their paths and work together to prevent any catastrophic collision. Pluto's orbital elements continue to intrigue researchers, and ongoing studies will help us better understand the future of this distant world. What the future holds for Pluto remains uncertain, but as we continue to explore the cosmos, new revelations will likely emerge, shedding light on the mysteries of the farthest reaches of our solar system.